Hi, my name is Ari.
And I'm Noam.
Today we'll be talking about our project, which was the implementation of a coherent Ising machine for the purpose of solving MIMO detection problems on an FPGA. And this work was done also with Han and Jure, who are part of our group. Okay, so a bit of an overview. So the problem that we're trying to solve here is called the maximum likelihood detection problem. And that's basically the problem in wireless systems where, say, at a base station, you receive a vector y, and you don't know, exactly what was transmitted. So you're trying to solve for this vector x, which, corresponds to the original value that was transmitted. And so there are existing approaches which are widely used, such as MMSE, which solves this problem using a minimum mean squared error approach. But this approach has some issues for low ratios of user to base station. There are also some existing work on using Ising machines for this stuff. But here we're talking about implementation of the DI MIMO algorithm, which breaks through some of the error floors that existed with previous approaches. And so our project goal here is to be able to implement on a larger FPGA a solver capable of solving 8,400 MIMO problems per millisecond. This is a number which comes from the LTE standard, and in so doing, we would be able to achieve state-of-the-art BER and throughput performance. And the real killer application of this is by implementing this on an FPGA purely, as opposed to traditional Ising machines, which are a mixture of optics and CMOS components. Such a solver would be immediately runnable on existing FPGA hardware in base stations.
Here we see the mapping from the MIMO decoding problem to an Ising machine problem. And the way this is done is represented by mapping the MIMO decoding problem to the canonical Ising model problem in which magnetically coupled spins are solved for. And then this is a way to represent this combinatorial NP-hard problem in the Ising model.
So the idea here is that we've mapped this optimization problem onto the Ising model. And so we can then, by finding the spin configuration, which minimizes the energy of the system, as described by our coupling matrix J, we're able to find a solution which corresponds to the original NP-hard optimization problem. So here, we're implementing the DI MIMO algorithm, which works by, instead of trying to use the Ising machine to fully solve the ML detection problem, it starts by seeding the solution with a linear time guess, either from MMSE or MMSE6, which are, effectively linear time algorithms, onto which we can calculate a correction. And so basically, we seed many solvers in parallel with different search spaces and initial spin configurations. Then we solve, each of these solvers in parallel finds a solution, and we pick the spin configuration which has the lowest Ising or energy corresponding to our ideal solution. And so the idea here is that once we calculate the final spin configuration, we can translate that back into a form which allows us to calculate the correction onto our original guess. So in the previous slide, we sort of saw more of a system level approach here, but here we're really focusing on the Ising solver component of DI MIMO. And so the Ising machine that we implemented here is implementing the amplitude heterogeneity control algorithm, or AHC. And so the idea here is that AHC defines a set of differential equations which evolve over time, and by basically iteratively solving these differential equations, we're solving the Ising problem and finding the spin configuration which corresponds to the minimum energy solution. So as we can see on the graph on the right, over time, the idea of AHC is that the spins bifurcate. So the spins either go to plus or minus 1, corresponding, as we saw earlier, to the magnetic couplings of spin up, spin down. So we see initially the Ising energy is kind of high, and over time the spins evolve, growing closer and closer to the correct solution until we see it flattens out, corresponding to the ground truth solution, and then the system stays steady.
Here we see a lower level depiction of the mapping from the MIMO detection problem to our Ising problem. So first we transform the MIMO inputs to a J matrix, which in addition to our initial spins gets fed into our AHC algorithm implementation in software. And then this is all sent to our FPGA, which runs the solver and then outputs the best spins, which we can then send back to the CPU. So here on the right, we can see the software implementation of this. And to recap, the way this works on FPGA is we have the CPU do the calculations to actually map the problem to the Ising model. This is then fed into the FPGA. AHC is run on the FPGA, and we obtain the best spins. Those are written back out to the CPU. Now, in the past, implementations of AHC have had scalability issues above 32 spins due to certain DSP constraints. So our optimizations aimed to minimize DSP usage using LUT approximations, as well as mapping. So this involved minimizing multiplications and mapping this logic to fabric as opposed to DSP units. So, for example,
so one thing we see here is, as opposed to our original Python implementation, which was a simulator for what we implemented on the FPGA, here we were able to implement everything as fixed point values. So the idea is, fixed point uses way less resources on the FPGA as opposed to floating point operations, and so we want to use fixed point wherever we can. In our case, most of our values were in 2.18 fixed point form, and one of the underlying themes of trying to optimize this design is that we're working with very tight latency constraints. And what that imposes on us is that we want to do as little intense computation in parallel, because the resource utilization really blows up. And in order to be able to solve these problems quickly, we cannot have the stages of the algorithm run for too long. And so all of our optimizations were centered around this idea of how can we do less compute intensive operations while keeping performance. So one of the things that we found in our Python simulation was that doing only signed bit matrix vector multiplication does not significantly degrade the solver solutions. And so particularly in the FPGA implementation, this is a huge benefit, because it converts what was previously a multiplication into basically just a mux and an adder. And we also, in some sense, benefit from the fact that we have noise as a result of these lower precision calculations. But because, in essence, these Ising machines are just a way of exploring many possible solution states, we can kind of leverage this noise and use lower precision calculations while still attaining the same final solutions. On the right, we see an example of one of our optimizations, which was we were able to map a certain multiplication from one of the update stages to a bit shift as opposed to a multiply, which was utilizing a DSP unit. So a bit about our results. So overall, we definitely saw an improvement in DSP utilization as we were able to move a bunch of multiplication. And confirming the initial functional correctness, we added a bit of extra logic, which upped our utilization, but which right up. We saw that the BER and spin outputs worked up to 2.18 precision, so anything above that worked as expected. And we're also able for multiplications per time step by replacing them with a bit shift, which over 200 time steps is quite significant. They occur at every time step, so any multiplication which we remove leads to a very significant. This what we did is we had a Python notebook which generated the instances, and then we wrote a test bench in HLS which called our function configurations, and then we ran it through and saved the outputs to TXT files. And then using our Jupyter notebook, we were able to run this in instances. We have 0-bit errors. And then here you can see, for example, us running something on the FPGA. So we start inputting J matrices and reading out spin outputs. So we're sending something in, and then we start to read back outputs.